Okay, so transition metals. So here we're going to start with transition metal ionic bonding. Transition metal ionic bonding. So to review, transition metals are the short columns smack in the middle of the periodic table. Okay, they're also called the B group. It's also called the D block because of electron orbitals. And the reason why transition metals behave differently than our main group A elements, meaning those tall columns, is because they can have valence electrons in two shells. So you can have a transition metal lose electrons from its outermost valence shell, or it can lose it from the d orbital. And so because they can lose valence electrons from more than one place, then in more than one way, then they can have multiple charges. Okay, so right now we know that if you are a metal in group 1A, you will always form a 1+ charge because you have one valence electron to lose. If you are a metal in group 2A, you will always form a 2+ charge because you have two valence electrons. However, transition metals, depending on their electron configuration and what they like to do, they can have more than one charge. So for example, copper, Cu, can be a +1 or a +2, just depending on how many it loses. Iron, Fe, can be a +2 or a +3, depending on how many it loses. Okay. Some metals that are really big and not necessarily transition metals, like tin, antimony, and lead, over in groups 4A and 5A, they act like transition metals because they also have d orbitals. So they can also lose electrons in more than one place. Okay, so what we're going to do today is figure out the method of, if I give you a name, how do you write a formula? And if I give you a formula, how do you figure out what version of this metal are we dealing with? How many electrons did this metal lose? Okay, and what is its charge? So we're going to follow the same kind of like pattern or notes pattern that we did before. And we're just going to start with a quick review of Roman numerals. So, Roman numerals. They're really important in transition metals bonding because they tell us something really important. So Roman numerals tell us the charge of our transition metals. So Roman numerals tell us the charge of our transition metals. So capital I is a 1+ charge. Roman numeral 2 is a 2+ charge. Roman numeral 3 is a 3+ charge. And then 4 is like an I and then a V, or it almost looks like the V means 5 and the one before it means 5 minus 1. So this is a 4+ charge. A V is a 5+, and then lastly, we're going to stop at 6, which is a V and then an I, is 6+. So you do need to know Roman numerals up to 6. And this tells us what the charge is. So just like I say, oh, you're a metal in 2A, you have a 2+ charge. Okay, well, you're a transition metal with a V, that means you're a 5+. So this tells us what the charge is. So if we're going to go from the name to formula, like we've done before, we're going to use these Roman numerals to get us there. Okay, so let's start with an example. Titanium 4 sulfide. Titanium 4 sulfide. Okay, so sulfide, that's familiar. We were dealing with that before. Titanium is a metal, it's a transition metal. And the new part is the 4. Okay, so this Roman numeral 4. This Roman numeral 4 literally tells us what the charge is of the titanium. So if we're going to kind of write out the formula the same way we did before, we would start with writing out our charges, or our symbols. So Ti is titanium, capital T, lowercase I. Sulfide is sulfur as an ion. This 4 right here, this titanium 4, tells us that the charge of the cation is 4 plus. It tells us. We don't have to do any guesswork. When we have a name and it gives us a Roman numeral, it'll tell you the charge of the cation. No guessing. And then sulfur, we know when it becomes an ion, has a 2 minus charge because it's in group 6A. And it will gain 2. So now if I crisscross these, remember, we are always forming a neutral compound. That's the goal here, where our pluses equal the minuses, okay? If I crisscross this, I would end up with Ti2S4. Can that ratio be reduced?
Yes.
Yeah. What can it be reduced to? TiS2. Okay? And if we think about this, we need a neutral compound. Okay? That's why all of these ionic compounds work the way that they do. Your plus charges equal your minus charges. So 4 plus and 2 minus, I would just need another 2 minuses to add that up to 0. So 4 plus a 2 minus plus a 2 minus would have our net neutral compound. That's why the whole reducing thing happens, is because you need it to be the lowest ratio that gets you that neutral compound. So to make a note here, transition metals use Roman numerals to show the charge of the cation. So instead of looking at the periodic table, like, okay, where is it? What group is it in? What charge is it going to be? The Roman numeral just tells us. So let's do one more example here. Chromium 6 Bromide. So take a second and think about this one. What would this be? As a hint, the symbol for chromium is capital C, lowercase r. Okay, so chromium then, first step is to write out our, oh my gosh, that's a terrible arrow. First step is to write out our symbols. So chromium is Cr, and bromine is Br. This 6 in the Roman numeral tells us that the charge of chromium is a 6 plus. That's what the 6 means. That means that this chromium lost 6 electrons. Bromine is in group 7A and will form a 1 minus charge when it becomes an ion. So if I crisscross this, or I'm thinking about getting this in a neutral compound, I have 6 pluses, which means that I need 6 minuses, right? So if I need 6 minuses, then I need 6 bromine or bromide ions. So if I crisscross, I get Cr, Br, 6. Okay, so going from the name to the formula is pretty straightforward. It's just whatever the Roman numeral is tells you the charge. Splitting them up is a little trickier. Okay, so we're going to do the same thing. Count out 7. 1, 2, 3, 4, 5, 6. Oop, 1, 2, 3, 4, 5, 6, 7. Because that's where our practice is going to go. And now we're going to split them apart. So splitting the compound into ions. All right, so we're going to write some steps out first. We're going to write some steps out, and then we're going to do examples, okay? Remember, ionic compounds are net neutral, meaning there's just as many pluses as there are minuses in terms of charges. And that is the thing we need to remember today. And it's almost like a little puzzle to try to figure out the charges of our cations, knowing that compounds are net neutral. So number 1, step 1, we're going to write the steps out, and then we are going to do some examples. Write the symbol and coefficient of each ion. Write the symbol and coefficient of each ion. Number 2, write the charge of the anion. And remember, the anion is the negative one. So write the charge of the anion. And then here's where the puzzle comes in and how you're going to solve the puzzle. Knowing that the total negative charge has to equal the total positive charge. So in order to figure out what that total charge is, we're going to 3 multiply the coefficient by the charge of the anion. And that will give you the total negative charge of the compound. So multiply the coefficient, meaning how many of the ion are there or is there, by the charge of that anion, and that will give you the total negative charge of the compound. And then number 4, we know that this is a net neutral compound. So the total negative charge has to equal the total positive charge. The total negative charge will equal the total positive charge because they add up to 0 in a neutral compound, neutral ionic compound. So number 5 then, once you know the total positive charge, divide the total positive charge, which is equal to the negative charge, by the coefficient of the cation to get the cation's charge. And we're going to do examples, so we're going to put these steps into action. Okay, let's start with making a table. So we have the formula, cation, anion, and our total number of ions. And we're going to make a table. Line across, line down, line down, line down. Okay, so example, the first one we're going to do. Sb2O5. Sb is antimony. Sb2O5. So, antimony is not in the transition metal block, but it will behave like a transition metal because it's so big and will lose electrons from more than one place. Okay, so step one, write the symbol and coefficient of each ion. Okay, well our cation is Sb, and its coefficient comes from the subscript, the same way we did before. So the coefficient of Sb is 2. Meaning I have 2 of them from this compound. Okay, we'll write the symbol and coefficient for the anion next. While our anion is oxygen, or oxide, in the 5 of the subscript tells me that there are 5 oxide ions. Step 2, write the charge of the anion. Okay, well we know oxygen, right? Oxygen is always the same. It's in group 6A, which means that it forms a 2- charge. So oxygen is in group 6A, which means it will always form a 2- charge. Okay. Now we need to think about this in terms of a net neutral compound. How many pluses are there? How many minuses are there? Because they need to add up to 0. So, step 3, multiply the coefficient by the charge of the anion, which gives you the total negative charge. Well, I have 5 oxide ions, and each one has a 2- charge. So 5 times 2 is how many? 10, right? And it's negative. So what we're saying right here is we have a total of negative 10 in terms of our charges. And I'm actually going to flip that. I'm going to do 10 minus, yeah. 10 minus. Okay, so we actually have 10 minus. We have a total of 10 negative. Now, if this is a net neutral charge, or a net neutral compound, that means my pluses equal my minuses. So how many pluses do I need to have then? 10. So if I have 10 minuses, I need 10 pluses. And now it becomes like a little puzzle. So that's number 4. The total negative charge equals your total positive charge because it's a neutral compound. So number 5, divide the total positive charge by the coefficient of the cation to get its charge. So if I have a total of 10 pluses and 2 antimony ions to split that between, that's going to tell me that the charge of my antimony is 5 plus. Each one is a 5 plus ion. So I have 2 antimonies. Each one is a 5+ ion. So 2 times 5 is 10. That's the only way I'm going to get a neutral compound. So if I look at my total number of ions then, I have 2 antimonies with a 5+ and 5 oxygens with a 2-. 2 plus 5 is 7. So there's 7 total ions. The tricky part of these is figuring out what the charge is of your transition metal. So if I were to say this compound out loud, I would say antimony 5 oxide. And if I were to write the name, I would write antimony and then a Roman numeral 5 in parentheses, oxide. Okay, let's do another one. SnO2. So Sn is tin, and it's just like antimony, where it's not necessarily in the transition metal block, but it behaves like a transition metal and can have more than one charge. So we're going to follow the same thing we did in the first example. Step 1, write the symbol and the coefficient for each ion. So my cation is always written first, so that's Sn. My anion is oxide again, and I have oxygen, or oxide ion. And this 2 as a subscript tells me that there are 2 oxide ions. Okay, same thing. Write the charge now of the anion. This one we always know because oxygen is in group 6A, so when it forms an ion, it will form a 2- charge. So now I need my total negative charge. 2 times the negative 2 is how many? I just used pink. Pink instead of red, I'm sorry. Okay, isn't it a 4- as our total? So then what has to be the total positive? 4+, because these 2 have to be equal. Your total positive has to equal your total negative because it's a neutral ionic compound. Well, if I'm looking at tin, there's only one tin ion here. So because there's only one tin ion, it must be a 4+ charge because there's only one of them. It can't share that charge with anything. So one ion of tin, 2 ions of oxide, 1 plus 2 is 3. There are 3 total ions here. Let's do another one. CuCl2. Step 1, split them up, write each symbol, and write its coefficient. So my cation is Cu, which is copper. There's only one of them because there's no subscript after the Cu. My anion is chloride, and there are 2 of them because there's a subscript of 2 telling me that I have 2 chloride ions here in this compound. Okay, step 2. Write the charge of the anion. Well, chlorine, we always know. Chlorine is in group 7A. It has 7 valence electrons. So to fill up its outermost shell, it needs 1 more. And when it does that, it forms a -1 charge. Okay, so now if I think about my total negative charges, I have 2 chloride ions, and each one has a -1 charge. So that's a total of 2- is my total negative charge. So if 2- is my total negative charge, then 2 positive, has to be my total positive charge because it's a neutral ionic compound. Well, there's only 1 copper ion. There's only 1 copper here. So because there's only 1, then it must have a 2+ charge. So when I say this out loud, I would say copper 2 chloride. because the 2 is telling me that it's a 2+ ion. And for our total number of ions, we have 1 plus 2 is 3. Okay, let's do one more. Ag2S. Ag is silver. Ag2S. Okay, step 1, split them up. Ag, S. Write the coefficients. Well, this 2 as a subscript tells me that I have 2 silver ions. There's no subscript after sulfur. That means I only have 1. Next step, what is the charge of the anion? Because we know that. Well, sulfur is just like oxygen. It's in group 6A. Will always form a 2- charge. So if I think about my total pluses and minuses here, I have 1 sulfide ion with a 2- charge. That means that my cation must have a positive 2 as its total charge. But I have 2 silver ions. So I have 2 silver ions, and they have to have a total of 2 positive charges. So each one then must be a +1. So if I were to say this out loud, I could say silver 1 sulfide. And my total number of ions, again, lucky us, is 3. So that's how we're going to solve transition metal ionic bonding in terms of writing it from a name. And then also if you're looking at a compound, how do you split them up and how do you figure out what that charge is of that transition metal?